Okay. Can you
So,
hear me?
yes, so please go ahead, Richard.
Yeah. Okay. Well, thank you, Jonathan, for the invite. As you said, I've been to Gothenburg recently. I haven't been to Virginia for I think maybe 20 years. So it's a great shame I can't be there in person. I enjoyed my visit last time I was there for sure. So, well, you see the title. We're going to talk about James Webb. It really is a very exciting time. I don't have to probably say that in pretty well every area. It's making a huge impact. So what I'm going to do is in 30 minutes, which I understand is the format, I will go through some progress areas, two in particular, which I'm pretty sure I can cover in 30 minutes. I have a third topic, which I'll come to, and if there's interest, we can have an open discussion about that, which is it may be relevant. So I have to start with this slide because it's what do we mean by high redshift? And if you look here down at the bottom here, I don't know if you can see my cursor. I was an undergraduate in the late 60s, and the most distant spectroscopically confirmed object was the radio galaxy 3C295. And if you look at it, it held a redshift record for nearly 20 years of 0.46. And through the years, through larger telescopes, CCD detectors, space telescopes, and now James Webb, we're up to, I think we're up to a redshift of 14. And of course, it's a non-linear scale because this is the age of the universe in millions of years. And so as you get to higher and higher redshift, this time is compressed. And so, but nonetheless, we're within sight of observing galaxies when the universe was only 2 or 3% of its present age. So the purpose of the topics I'm talking about is all to do with the earliest objects emerging from darkness. So this is euphemistically called cosmic dawn. This slide, obviously from a cartoon from Avi Loeb, who has done a lot of distinguished work in this area, even if you're not completely happy with some of his more recent antics in astrophysics. There's dark clouds here, which are forming around dark matter, which fractionates from the early universe before recombination, and so is already in place when the hydrogen clouds atom form for the first time. These hydrogen clouds become gravitationally unstable, they collapse, they heat up, of course, and they ignite nuclear fusion in star clusters. And these stars are very, very hot, actually, for a given mass compared to stars in the Milky Way, because there's no line blanketing, of course. So they photoionize the hydrogen and create these ionized bubbles, which become more numerous and grow with time as more galaxies form. And then the universe is completely ionized. And it's been known since the 60s that the universe in deep space is fully ionized. So the mystery is, is this theoretical picture correct? And to do that, we need to understand the properties of galaxies. We need to understand how many there are, their abundances, their ionizing radiation fields. We need to understand the AGN component, which we think goes hand in hand with the formation of galaxies. And so this is the territory that we're going to talk about. These are incredibly important and big questions that motivated at least one pillar of the James Webb Science Case as long ago as 1996. And of course, the launch in Christmas 21 was a huge success. So I want to start with what we know already about reionization. And, none of this has really been changed by the first couple of years of James Webb. I'm going to start with when did reionization end? And the state of the art here is still the Lyman alpha forest seen in quasar spectra. So what you see here from a paper from one of my former postdocs, Sarah Bosman, who's now in Heidelberg, is you know, the light of a quasar, background light of a quasar that passes through the IgM. And as you can see, the spectrum of the Lyman alpha forest varies from sightline to sightline. And you can see you probe a single 1D slice through the universe. And where you see the signal, then the hydrogen is, of course, not completely absorbing. And so it may be partially ionized. Where the quasar light is completely cut out, then the neutral fraction is fairly high. And so the fact that you see this scatter is telling you at these redshifts that there's still patchiness in the hydrogen absorption, even at a redshift less than 6. And the quasar people have just completed a very big ESO program called XQR30, which added to earlier samples. The 30 is a 30 X-shooter spectra of redshift 6 quasars, and the total now is 67 quasars. And this is the state of the art in looking at the end of reionization, again from Sarah's work here. And what you see is, it doesn't go beyond a redshift of about 6.3 or so. And that's because there still aren't many quasars beyond a redshift of 6.5 that are suitably bright. And this is not a very sensitive technique once you get up to neutral fractions of, say, 1% or so. In other words, the sensitivity, just, a very small fraction of neutral gas can completely cut out the Lyman alpha forest. So you can't really extend this to higher redshifts, sadly. But what you can do is see that the scatter starts to disappear at around a redshift of 5.3 or so. So they tend to believe that reionization peters out. Of course, it's not a sudden moment. It sort of peters out by a redshift of somewhere between 5.3 and 5.5. You can complement this with Lyman alpha in emission in galaxies. Lyman alpha is the ground state line, of course, of hydrogen, and it's a resonant line. It's easily scattered. So if a galaxy is producing copious amounts of Lyman alpha in a neutral region, then the visibility of the line is very poor. It's scattered so much that you don't see. It's weakened a lot. Whereas if it's in an ionized bubble, then the Lyman alpha photon can freely travel. It's not scattered. And by the time it reaches the end of the bubble, it's Doppler shifted out of resonance by the expansion of the universe. So Matt Schenker, who was my student with Dan Stark, we did this with Keck. We just championed the idea of looking at the fraction of galaxies that showed Lyman alpha. And as you can see, it starts to drop. It's a qualitative, I wouldn't say it's a quantitative measure of the neutral fraction. But what's changed, zooming ahead to James Webb, is that we now have spectra not only of Lyman alpha, but also the Balmer lines like H beta and H alpha out to redshifts of 9. And because these are hydrogenic lines and only Lyman alpha is resonantly scattered, recombination theory tells us what, if we measure H alpha or H beta, we can get an idea of what the intrinsic Lyman alpha emitted by the galaxy must have been. And that allows us, therefore, to calculate the fraction that managed to get out into the intergalactic, through the intergalactic medium, which is, of course, an equivalent measure of the neutral fraction or the ionized fraction in the intergalactic medium. And so this very nice work from another one of my former postdocs, Ayush Saxena, who's now in the JADES team, luckily at Oxford, he calculated the escape fraction, and you can see it's really dropping from, a very high value when the universe is fully ionized and out to redshifts of 9, it drops quite sharply. So we don't yet have, unfortunately, the observational history yet of the reionization era. We've got constraints on how it ended, and they're shown by these various quasar and Lyman alpha fraction tests. There's the Planck measurement as well, which that doesn't really give us the shape. It just gives us a rough measure of the halfway point. And there are two curves shown here. One is the curve that Brant Robertson and I worked on when we thought we had a good census of the Hubble abundance of galaxies. And we made some assumptions about their properties. And it was a naive paper because we assumed all galaxies were equal. Irrespective of their luminosity or redshift, they all, more or less had a certain population of hot stars. And we got this curve that matched the Planck data, matched the abundance of galaxies and so forth. And Rohan Naidu at CFA, thinks that this curve doesn't fit very well. If these measurements of data beyond lower than a redshift of 7 or 7.5 or so, suggest that reionization ended more quickly. And that's very exciting because it may be that that's due to AGN developing. And of course, that's one of the things that James Webb can really constrain. So before I get to James Webb, I want to just say how far we got with Hubble. And we'll come back to this field, the ultra-deep field, later. In 2012, we pulled the stops out with the Wide Field Infrared Camera 3 and added it to all the data that had been taken in this unique field before. And for the first time, we found 7 objects beyond a redshift of 8.5. And the most distant, which was highly marginal, actually, was this object, which was only seen in one filter. And we had this, it's truly audacious to estimate a photometric redshift for a galaxy with one detection in one filter, but that's essentially what we claimed at a redshift of 11.9 plus or minus 0.3. We assumed that the non-detections in all the other filters was due to the Lyman break cutting off the signal. So I will kind of come back to this object. The other technique that has been highly successful is strong gravitational lensing, the frontier fields. If you haven't kept up with gravitational lensing, it is truly astonishing what's possible now with James Webb and even with HST. This is one of the 6 frontier field clusters. So the aficionados can find 180 multiple images in this cluster. So they can use that to construct the mass distribution and hence the lensing power. And of course, in certain regions of these clusters shown with the lines here, the caustics, the critical lines, the magnification can be very high. So these 2 techniques gave us the first census pre-James Webb, but there was a controversy. Everybody agreed out to a redshift of 8 that the number of galaxies was falling. This is a logarithmic scale, so it's a really quite a marked drop. But in terms of predicting when it all began and when cosmic dawn, there were 2 groups, and the Edinburgh group led by Derek McLeod, they believed that the decline was relatively smooth. Whereas the Geneva group led by Pascal Oesch and Garth Illingworth and others thought that the decline was steeper. And their motivation for this, and we'll come back to this, is this curve here called halo evolution seemed to fit the data, very, very well. So, unusually for observers, they thought they were right because it agreed with the theory. Often observers are delighted when their data doesn't agree with the theory. So we're going to come back to this discrepancy. You might ask, why was there such a scatter here, even though both groups were analyzing the same Hubble data? And the answer is they disagreed on which photometric redshifts were reliable, which objects should be binned in which redshift bin, et cetera, et cetera. And as you can see, the numbers of objects was really very, very small. So here we are. If you look here, I was the only European on the Dressler committee in 1996, which wrote this very nice report, HST and Beyond, which proposed what was then known as the next generation space telescope. And my God, it's taken 25 years to launch, and it's almost as amusing and sad in many ways as the story behind Hubble, of course, which was envisaged in the 1960s and didn't get launched until 1990. I was privileged to see James Webb in the Lockheed Martin clean room in El Segundo in February 2020, literally the last trip I made on a plane before lockdown and the pandemic hit. And it is a religious experience, I would say, to see this thing. There's a human here, so it's just astonishing that this thing works so well. So what's happened is there have been over 200 archive articles on distant galaxies in 20 months. It's very hard to keep up. And I'll say tactfully that not all of them are of equal quality. The main advances are, obviously, it's sometimes said that it's a successor to Hubble, but it isn't really. It's you might say it's a milestone successor to Spitzer, because it's primarily an infrared telescope. Obviously, it's got a larger aperture, and therefore it's got a better angular resolution, something that really isn't realized by many people, that for studying Cepheids in nearby galaxies, for studying lensed objects, that additional factor of 3 resolution gain is really amazing. But its main emphasis is it goes beyond the limit of 1.6 microns of the Hubble. And here you can see that not only are there broadband filters, but there are medium band filters. So for those of you who study spectral energy distributions, it's almost as good as spectroscopy, because you can see little excesses in the medium band filters, that can give you measures of H alpha or oxygen 3 and so forth. But it is a genuine spectroscopic telescope as well, and that's probably its biggest feature, because its aperture is large enough to exploit it. It's outpacing telescopes like Keck. So, famous instruments like Mossfire on Keck, cannot compete with spectra like this galaxy shown here at a redshift of nearly 8 or so. So the first highlight is here's Derek McLeod. He doesn't have any hair anymore. I think the stress of working on James Webb, has taken its toll. He's completely bald now, but here he was in the earlier article that we wrote together. This was one of the early immediate results, and each color here is, apart from some of these points down here, which are Hubble data, all of these points down here are independent analysis of the first public data from James Webb. And here's that theory curve again. And the boundary between JWST and James Webb, is somewhere around here. Derek's points are here, the two, and this one is more tentative. And as you can see, the first glimpse is that this argument is settled. The curve carries on, and so we see galaxies out to redshifts of at least 13, and I'll update you in a minute on that. And this has been one of the main sort of surprises or progress, that the theory doesn't match. So we'll come back to this theory in a moment. So I'll come back to exactly all of these possible explanations. But just to list them, these are still at the time, these were still photometric redshifts. One idea is that galaxies are more visible because they're dust-free at these early times. Dust is produced very quickly, but maybe radiation pressure in the early years pushes it out. Alternatively, it may be that the galaxy doesn't develop its feedback cycle early on because the star formation is so intense in such small objects of low mass that the gas can cool very, very quickly, and not be inhibited by feedback until later. you know, one can twiddle with the IMF, and of course that's always dangerous, and you can pretty well get anything you want. And then another idea is that these objects are being seen at a special time when they're bursting, and so they're not really consistent, you know, with their quiescent luminosity. So those are the basic ideas. Well, since that early time, I want to highlight two papers, one that I've been involved in, which are based on guest observer data and GTO data. Well, no, both developments are guest observer data. We wrote a successful cycle 1 proposal called Primer. The PI is Jim Dunlop. And I'm on it with Garth Illingworth and a few others. And Callum is a student of Jim Dunlop's at Edinburgh. Primer is the largest imaging survey in cycle 1. It's much bigger than the GTO team. It's not quite as deep. Here's another early release science, NG Deep, which covers. And so what we did was combine all this area to make what we would call the widest area in searching for high redshift galaxies. It's tiered. Some of the data is deeper in smaller areas, so that's helpful. So it gives you dynamic range. You can see all photometric redshifts, of course. You can see the range in the luminosity function at redshift 12.5, 4 magnitudes. And you can see that the data points continue this extension and out to at least a redshift of, this is the redshift 12.5 point. And there's a hint that there's a paucity of objects. I wouldn't say, you know, that one would get too excited by this downturn. Astonishingly, there are 2,500 candidates beyond a redshift of 8.5 in this area. And if you compare that with Hubble, where there was something like maybe 15, or, well, remember in that ultra deep field in 2013, there were only 7. So that's the kind of progress that we're seeing. The other development is another GEO program, but this time by the JADES team. As if they hadn't had enough data, they decided to go for GEO time in cycle 2 and pull the stops out in one area around, or 2 areas around the ultra deep field, with a 7-day exposure in these 2 areas, a parallel, and then they switched it round. It's 9 arc-minutes squared, so compare that with 400 to give you an idea. So this is, you know, go for broke, very, very deep. Probing a redshift of 12 to 20 with 14 filters. And they located 11 candidates beyond a redshift of 11.5, of which 8 of them they think are reasonably confident. In terms of pushing the frontier, you know, beyond this point here, they found 3 galaxies that they think are at 13.5, 14.4, and 14.6. And there's a rumor in our community that we're going to see one of these has been spectroscopically confirmed. I don't know which one it is, whether it's the 14.4 or the 14.6. What you see is the photometric redshift for this object that's claimed to be at 13.5. This is the James Webb data. The red points are the Hubble data. You can see the error bars are much larger. It's not completely bulletproof, in my opinion. You know, this peculiar SED behavior here doesn't seem to make sense. This point here shouldn't be detected. So I don't know what's going on here. And if you read the Robertson article, they're very honest about these 3 objects. They discuss them in some detail. Well, it looks like at least one of them's right. Although they were sensitive out to this redshift range, they didn't see anything beyond this. And they make some statement, you know, that this could be quite important. Well, I'm running out of time. I can see I want to cover AGN. So let me just say, you know, photometric redshift errors, I don't think are that worrisome. This is not completely up to date, but this is what's been done by James Webb so far. And you can see, there are a few oddballs, but it's pretty tight. And I'm amused that this object that was detected, here it is again, we claimed very bravely it was 11.9 plus or minus 0.3, and it is astonishingly, I never would have believed it, that we found the most distant Hubble galaxy in the ultra-deep field. Its spectrum here from Emma Curtis Lake in the JWST team, 11.6. So I'll whiz through dust-free galaxies. Andrea Ferrara has proposed, I gave you the idea, that dust is driven out in these early periods. His argument is that there's a threshold where this happens, and he calculates this mathematically. He thinks that it should switch on earlier than a redshift of 10. And this is where you get super Eddington outflows. So what he does is he calculates the specific star formation rate and calculates whether it's enough to drive the dust out. And he thinks beyond a redshift of 10, it would be. And so the question for the observers is, is there anything happening here? Is there any change in this region where you don't agree with the theory? And one way to do this is to look at the ultraviolet colors to see whether the dust continuum. So this is known as beta. Beta is a measure from about 3,000 down to Lyman alpha of the slope of the UV continuum. And there are two important papers, one Fergus Cullen at Edinburgh and Michael Topping at Arizona. And they're very similar. One looks at public data sets, the other guy is a member of JADES, and they don't see a very sharp, they see that beta declines. If this concentrate on this panel here from Mike Topping, the beta, the more negative it is, the steeper the UV continuum. And you can see it is getting steeper, but there's no sudden change beyond a redshift of 9 or 10. And the theory limit for a dust-free stellar population, if you just go to star, whatever that code is, starburst 99, that's right, you get, -3, but then you have to remember that these early galaxies have a nebular continuum. And if you add that in, it's about -2.6. So, you are heading to dust-free stellar populations at early times, but it's not as if here's Cullen, there's maybe a marginal change here. So high Z galaxies are dust-free, but there's nothing unusual going on. It's a continuous trend that goes all the way down to lower redshift. So I really want to say a few words about black holes, because I know this is of interest. The challenge, how on earth do we get 10 to the 9 quasar supermassive black holes by a redshift of 7 or so? We need to find them at earlier times and measure their black hole masses. And you can do this by spectroscopy. You can do this by X-ray detection, but generally they're too faint unless you have strong lensing. And as you may have seen, we're very keen on variability. You do need a long baseline in time, and ultimately all the variables need to be followed up to be sure they're AGN. Well, the main results are that there are some very controversial claims for AGN, in my opinion, at redshift 10. I hope there aren't people on the call who are on those papers, but if they are, I'll try to be as tactful as I can. There are more robust examples now out to redshifts 8. There is a newly discovered population of dust-obscured AGN called little red dots. And the exciting news is that if you believe the mass of the black holes, and we'll come to that, then they lie above the black hole mass stellar mass relationship locally, suggesting that they've grown faster at earlier times. So just to go through some of the papers, Yuchi was a postdoc with me in UCL, and during the pandemic he got a permanent job in Japan, so he left. He did the earliest census of broadline AGN. He looked at all the spectra in the public data, and here's the He didn't find very many. He only found 10, but it's 5% of the spectra that he looked at, which is a much higher fraction than what you see locally. He estimated their black hole masses from, the relations that we use locally by Green and Ho and Volontieri et al. And so forth. And, these masses are in the region of 1 million to 10 million solar masses, and they lie above the relation between the mass of the black hole and the mass of the stars in the galaxy that we see locally. He estimated their luminosity. These are faint AGN, of course, and he found that there are many more faint AGN than had hitherto been found. This is, I think, a very good example of beautiful James Webb data. This is from the Uncover team. This is a redshift 8.5 object. You can see beautifully the broad H beta. You can't get H alpha at this redshift. It's out of range. But you can see the broad H beta and the narrow O3. The broadening is 3,400 kilometers per second. That is probably much larger than you would ever get from outflows. And here's the galaxy on the here's the local relation again. And the galaxy is, way up here in its black hole mass, 30% of the stellar mass. Now, I asked Lewis Ho, who's a sort of world expert on this, do you believe these black hole masses? He says, they're much more uncertain, perhaps, than the papers think. But on the other hand, the errors, are unlikely to be much bigger than about a factor of 5 or so, just from bolometric arguments. So, you're not going to bring this data point down to here, I don't think. So the little red dots are a new population, and they were found by looking at H alpha in slitless and other data. And Mate, now in Austria, then looked at the images and found they're all very, very compact. You can hardly see the host galaxy. They're point-like sources. They have broad lines. Not all of them. Some of them turn out to be brown dwarfs and so forth, but, which also show H alpha. Jenny Green got spectra of 17 of them and found 11 of them were broadline AGN. And they have a very characteristic SED. They're very red, obviously, as you can see in the rest frame optical. They show H alpha and H beta, but then they have a UV upturn, and the slopes are very different. And the origin of this is debated, whether this is this starlight. Some people believe this is starlight, but most people say, well, it can't be because of the broad lines. There's one object which is lensed by Furtak et al. It's at a redshift of 7. And you can't, because it's lensed, you have an exquisite estimate of its size, and it's less than 30 parsecs. So you might argue there's not even a host galaxy. It could just be, a non-thermal radiation from material falling into a black hole. This is a very interesting object. So if you haven't read that paper, go and read it. Well, bring you up to date. I thought this paper would be on the archive now, but Dale Chevsky had access to the primer data, which is still under wraps. And so we've worked on this together. And this is a 500 arc-minute square search. And he's found 340 little red dots. And their redshift distribution, although it would be sensitive all the way down to low redshift, they seem to switch off at redshift 4 for some reason. And it's clearly a new population, and we don't really know what's going on here. It may be that at early times, star formation is very compact, and the metals build up in the bulge, and the host object is the source of obscuration. It's not the nuclear obscuration. And then, as the universe expands and star formation moves to larger scales because there's angular momentum maybe, and the host obscuration isn't so important. And so you basically lose these objects. We don't really see any of these objects at low redshift. Jonathan, I run out of time. I could
It's
talk
okay,
about
Richard.
the
You can go another, maybe go another 5 minutes, and then we can just
I'll
transition.
just another 2 slides then. Okay. And then I'll tell you what I would have talked about if I could speak even faster. Well, I'm skeptical of this. I'm sorry. This is a cluster, a frontier field cluster, very famous, and was the source of the pointing for the GLASS early release program and Uncover. And the team claim that there's a 4 sigma blip in the X-ray signal in the cluster. So the cluster is an X-ray emitting cluster. You can see it's extended here. And there's this blip here. It's 4 sigma in X-rays. And they went and looked, what could this be coming from? And they found it was a positional coincidence with a galaxy at a redshift of 10.3 that was identified photometrically by the GLASS team led by Tommaso Trio at UCLA. And so they thought, wow, this is a lensed X-ray emitting AGN. The argument, well, if they have to estimate the mass of this black hole somehow, and they take the bolometric luminosity in X-rays. And they have to make a huge correction for that. And then they finally got observing time to get the spectrum of the galaxy, which the GLASS team didn't have. And there's no evidence of any AGN activity in the spectrum. So then they said, well, it must be obscured. So I'm not convinced. I think it may be a positional coincidence, but if it's correct, it's dramatic news. And if you buy it, then you should read Priyo Natarajan's paper, because you cannot have a mass like this at such an early time from stellar black hole masses. This would have to be evidence for some direct collapse black hole. Oh, I should say, and if that wasn't enough, a few days ago they claimed a second object, another X-ray blip, which is not quite so near another galaxy that was found by the GLASS team. So if you're enthused by this, you should read the second paper as well, which is not accepted yet. This paper got in Science magazine. This spectrum was one of the highlights of the first year of James Webb. I never believed that I would see a spectrum of a redshift 10.6 galaxy that has all of these lines in it. This is just beautiful data. However, Maiolino, who's on the JADES team, believes that these high ionization lines, nitrogen 4, carbon 2, this outflow, which is, you can see this P Cygni profile here, and the high density of gas, which comes from the doublet ratios of nitrogen 4 and nitrogen 3, points to a black hole. Well, no, this is controversial. This has now come out in Nature, I think. But this galaxy has a number of interesting features, including a high nitrogen abundance, which many people argue is a high density of hot, massive stars, which are likely to form globular clusters. So the AGN in this is not so clear cut. And let me end with our famous work from Matt Hayes, Jonathan, and I, and colleagues in Gothenburg and elsewhere, variability. And so it's something like over a decade since the Hubble Deep Fields was observed. And so we went back and got time to visit it again in one filter. And we found 73 variables, including several AGN. But interestingly, we found 3 objects that are varying. This is perhaps the most compelling. This is, what light curves look like in rest frame years. So it doesn't look like you could explain this object with a supernova. And it's a surprisingly, I was pretty impressed by Matt's analysis because it's a surprisingly competitive constraint on the density if these are AGN. So, we're trying very hard to get more repeat fields in the frontier fields. We're trying to get observing time to get spectra. We've got some spectra, some of them are candidates, but that hasn't been analyzed completely yet. So I'll stop there. What I was going to talk about, if I managed to squeeze it in, was, would we recognize a POP3 system? So I'll leave it there, Jonathan, and hand over to you.
Great, thank you very much. So now we can.
Shall I get out of share mode?
Keep the slides on the screen. Often the questions will relate to your slides. So.
Okay, I won't be able to see anybody, of course.
Yeah, I'll try and moderate here. So raise your hand in the Zoom if you'd like to ask a question to Richard, and maybe why don't you go ahead, Richard, and just say what you were going to say about POP3 for a couple of minutes while people are thinking of their questions.
Well, it's going to be very hard. I think numerical simulations of, how quickly POP3 disappears suggest that, these halos, these mini halos, are really low mass at these early times, a few hundred solar masses. The galaxies are, 20 to 50 times smaller than they are today. So pollution from supernova that happen within, say, 5 million years or so means that, metals pollute the system very, very quickly. And, even if you find POP3 areas, and there have been claims, which I could come to, two claims in the literature that, they found POP3 systems. They may be coeval with, population 2 systems. So, that wouldn't satisfy the definition of cosmic dawn. It would be interesting to find pristine areas. There have been claims for pristine gas at much lower redshift as well. Here are the two claims. Our friend Maiolino again found this helium line, which is at a precise redshift of this galaxy whose spectrum I showed you at 10.6. It's very, you could argue it's very weak. The fact that you don't see other lines is his claim. He's got observing time to go back and look at it again. So, you can see the significance here. It's not, I wouldn't write home to your mother about it, but this, line is, it's tantalizing that it's at the right redshift. And then Eros Van Zeller, and this goes back to lensing again. These are objects that sit very, very close to the critical line where you have magnifications formally of up to infinity. This one is a redshift 6.6. Where is it? I can't see it here now. It's in one of these two here, L1 and L2, I think. And there's, he's got spectra and he doesn't see O3. So it's a system at a redshift of 6.6 and his metallicity is less than 0.3% solar. And that's, 0.0, let's see, 0.0, yeah, 0.3% solar. So that's pretty tantalizing. But, I think it's going to be very difficult. The time window is short. And, to find an object, you have to demonstrate there's no metals, and that requires exquisitely deep. So I think this is probably going to come with SKA low, where, we see this the 21 centimeter absorption due to Lyman alpha coupling, and the redshift range that SKA low will achieve will be, we'll be able to monitor that with James Webb.
Mm-hmm.
Okay, I'll stop there. I got through pretty well everything, actually.
Great.
Sorry if I went too fast.
No. So I'm not seeing any hands in the Zoom, so please do raise them if you have a question now for Richard, but I can ask another one. I mean, so the role of AGN in reionization, and we were talking about it here perhaps a little, is there, I mean, I recall helium reionization happens much later and was...
That's right. And that's dominated by AGN. Yeah.
Right. But if AGN are playing a significant role early on, is there a way we can would there
So
be?
the latest is, I would say, the latest is this luminosity function here. And so, you could imagine that the escape fraction of ionizing radiation, is at least 50%, in many of the galaxies with AGN. So this is the luminosity function from the little red dots in the Primer survey, between 6.5 and 8.5. This black curve is the Lyman break population. So you can you can compare the two if you like. Oh, I'm sorry. No, it isn't. No, I'm sorry. I'm wrong. Let's go back to Harikana. Where's Buins? Yeah, these are the normal galaxies.
Mhm.
Okay. And these were the first estimates. So you can see, it's about this. They're still, even though they're more numerous than we thought, they're still a factor of 10 or so lower than, the normal galaxy population. So even if you gave them a huge escape fraction, like 100% or 50%, then their contribution to reionization would be at about the 5 to 10% level. Important, but not dominant, like Piero Madao
Mhm.
claimed many years ago.
Mhm. But would there be a prediction for helium reionization that happens earlier, like an early phase of helium reionization, or what could you
Oh,
learn
I see. No, I don't. Yeah, I don't think so. I don't think anybody's looked at that. I thought the helium reionization, obviously you need much more energy, and so that's that's really requires quasars, I think. But I'm not an expert on helium reionization, I have to admit.
Mhm. Mhm.
But I thought helium reionization was really well understood, um, just from the numbers of quasars.
Right, at earlier, around redshift 4 and
At
some,
late times, yeah, redshift 3 to 4, yeah.
but if there was a,
But you're thinking there might be an early phase of helium reionization?
well, that would be a difference, that would be more sensitive to the impact of AGN. Um,
Yeah, I don't know. I haven't looked at that, but that's an interesting idea. Yeah.
okay, Brant, you had a question then, and then Gina.
Ooh, okay, there we go. I was all blurry for a second. Yeah, thanks for the great talk. You talked a bit about the escape of ionizing radiation in terms of photon radiation, but has there been a lot of investigations into the contribution of particle radiation from AGN or other central kind of energy sources? Because those can not only escape just normally, but they can be advected out of the galaxy and potentially escape even
Yeah.
more easily
Yeah.
than the radiation.
Yeah. Thanks, Brent. That's a very good question. So the assumption has been, you're right. There are many articles on annihilating dark matter, elementary particles, X-ray binaries, and their contribution to reionization. The dominant assumption has been, can we make galaxies and AGN work? In other words, why? Only if we fail to do that, would the mainstream astronomers consider some of these more exotic explanations, like elementary particles or decaying dark matter or something
Well,
like
so I'm
that?
not in this case, I'm not talking about elementary particles, but just accelerated particles from either from the
Yeah,
star formation or from black holes that are just AGN activity accelerating, protons
yes,
or
there
something.
are. Yeah, yeah. So the papers that have discussed AGN contributions take that into account. It's not just,
Okay.
radiation fields. And
Okay.
generally that's where this 10% number comes from, but it's not been updated. There haven't been many articles updating with the James Webb luminosity functions because the field is changing so much. I think it'll be interesting, when Dale Kachevsky's paper comes out, because it is it is likely that a very high fraction of these are AGN. This is just to stress, these are still photometric candidates, but the criteria that are used here, the red slope, the blue slope, and the compactness, gives you an 80% success rate in the spectra that we currently have of these little red dots. So this paper is sort of state of the art in the number of low luminosity AGN at the end of reionization. So the question is, if the AGN aficionados put this into their models, as you suggest, then, would it explain this rapid, decline here? In other words, where, thinking that AGN start to make a, significant contribution to reionization at below a redshift of 8 or so. And Dale's data is just perfect for making this calculation.
Great. Gina, another question?
Yeah, hi. So I was wondering, you mentioned these different theoretical explanations for the very distant luminous galaxies. And I was wondering what would we need to measure to distinguish those scenarios?
Well, I think it's fair to say you can fit anything if you're willing to tamper with the IMF. And you can look at Harikana's paper, and he manages to, to fit this extension by just switching on and saying when the metallicity gets low, massive stars form, more easily. They don't fragment. They can cool, without the metals. And so you can get 300 solar mass stars, 500 solar mass stars. And obviously you jack up your ionizing radiation field, you increase radiation pressure, so you improve your escaping radiation as well. So, this is you can easily turn this on and fit the data. You can play with feedback. If you switch feedback off, the numerical simulators play this game all the time. They can adjust the knobs on their feedback mechanisms to make galaxies more luminous. So I think it's going to be very hard. I focused in my talk on dust because it's one of the easiest ones to test. We could test for heavy IMF with line ratios, and there have been some papers on this, that some of the line ratios that people see, and this nebula continuum, if there are lots of hot stars, massive stars, then nebula continuum is important. So let's talk about that. If you increase the nebula continuum, paradoxically, it's redder than starlight. And this is 2 photon emission and nebula continuum, free and bound free. And so if you can see, and they have signatures. So there's a paper by Harley Katz where you can see a downturn in the 2 photon emission turns down at around 1400 angstroms or so. And he claims to see this downturn in some of the high redshift spectra. Let's see if we can find, do you see this turn here? Can you see my cursor? There's a downturn here, which is odd. Why is this is this a damping wing or not? And so, there are cases where this downturn could be nebula continuum, which might be an indication of 2 photon emission and very, very massive stars. But to answer your question, I think it's one of these things where the theorists have so much freedom that they can always fit the data, and it's going to be very hard until we come up with better spectra.
Great.
Very good question, no? Yeah.
If there are more questions, please raise your hand. Let me ask about, just related to this, then, if we have a very deep spectrum of a redshift 10 or higher AGN,
Yeah.
So in the where people would normally study the damped Lyman alpha forest, is it completely hopeless there to see anything, or can you see evidence of the local reionization bubble around the source?
Yeah, so this is, this is state of the art, really. I can't remember, this is like 20 hours, I think, but this is an exceptionally, it's the most luminous object beyond a redshift of 10 that we know. If we got, say, 50 hours, which Maiolino is going to get in cycle 3 for his AGN in this object, and I think he'll also get, simultaneously, we'll see whether this helium-2 is there. One thing you can do is, of course, look for the damping wing more accurately. If you have higher resolution, you can check the line ratios much more accurately. You can look for broad lines and so on. So there's quite a lot of spectroscopy approved in cycle 3. So yes, it's going to be valuable for AGN physics. We're pretty sure that the neutral fraction at redshift 10 is quite high. You can see this object doesn't really have a prominent Lyman alpha, and our object at redshift 12. Let's go back to it. The object that we found. Where is it? This object. It doesn't have Lyman alpha either. So, all you can do is measure the break and make sure that it's, So I don't think there's much interest in measuring the neutral fraction at high redshift. I mean, we're pretty confident because we don't see Lyman alpha that it's, the bubbles are not there, they're not very big at that epoch, probably.
So
at lower redshift 7 to 10, yeah, that's very exciting, measuring the bubble diameters and so on. If you can trace many objects close to one another in a cluster, you can start to measure the sizes of the bubbles.
So there'd only be an upper limit constraint on the size of the bubbles. So now you're saying from these high redshift.
There are papers that claim bubble sizes already. At redshift 8, yeah. Ryan Ensley at where is he now? No, he's at Austin, Texas. So he's written some very nice papers correlating Lyman alpha from individual objects and measuring bubble sizes. And pretty soon SKA, of course, will start to chime in, and that'll be fantastic. Once we have, it's fantastic that JWST is going to be around for 20 years because it'll overlap with SKA. And that wasn't guaranteed. The guaranteed lifetime of James Webb was 5 years, optimally 10, and now it's 15, optimally 20, which takes it well into the SKA era. So that synergy is going to be great.
Great. We're going to finish in a moment, but Tom, go ahead and ask a question.
Perfect. Thanks for this great talk. I'll try to keep it short. You mentioned one of the explanations in explaining these distant bright galaxies as being the uncertainty in the redshifts. And then particularly when I was looking at the beta UV slope, like if you can go one slide back, Steve Sargent and I, the spectroscopic versus photometric.
I'm sorry. Yeah, that one.
Yeah, we did a small test showing that it's Eddington scatter that's pushing all these galaxies to be slightly biased high towards photometric redshift.
Right.
Is this then the underlying argument towards maybe why we're finding all these bright or very blue beta UVs at high redshift, that we're just simply picking up these scattered ones?
Yes, I think Tom, there is that effect, and it's you can see it in the figure in Cullen et al., which I don't have at hand. If you go to Cullen's paper, Fergus's paper, he has of his 176 galaxies, some of them have spectra. And there's a very nice paper by Guido Roberts-Borsani, which stacks all of, and if you look at that, he measures beta from the stacked spectra. and he compares that with the photometric data. And there's that upward trend that you mentioned. So I think you're right. And there's 3 pieces of evidence for that now. So, so this changes, as always, this changes some of these arguments in these 2 papers, I'm afraid.
Are they bright enough that we can detect their redshift spectroscopically in the ones that we're seeing in this? Typically, they're very, very faint, these objects, right?
Yeah,
Beyond the scope of nearest back.
yeah, well, as I think I said, the only available data is UV, and we must resort to photometric measures to get large samples. The spectra, I mean, the closest we've got is Robert Borsani's stacked spectra, but they don't, he has very few beyond a redshift of 10, a handful. So if you look at his paper, he does produce a stack at various redshifts and measures beta, but by the time he gets to redshift 10, the sample is very small. But it's going to grow, it's going to grow with time.
Exciting.
Very good then. Well, we should close up the hour here, but so let's thank Richard again.
Thank you.
Yeah, that was a great talk. I'll stop the recording.